Hello. In today's video, we're going to talk about, I'm going to talk about what happens with two-dimensional vectors and opposing forces, and how to use unit vectors and scalars to handle this, and sum of vectors to handle this. So first, to understand the problem, there's inexplicably two cables that are holding up a traffic light. And it's known that the force or the gravity or whatever the weight of the traffic light essentially is 125 newtons, and it's in the downward direction. So there's a downward vector pulling, essentially gravity pulling the traffic light down. Of course, the traffic light doesn't fall down because it's held up by two wires. In vector language, essentially, we should understand that each of these wires is contributing to holding or opposing the force of gravity, weight of the traffic light. So the idea is that there is one force downward at 125 newtons, and then the sum of the scalars of these wires will add up to oppose that negative 125 newton force. So essentially, if we take a vector in this direction and scale it up or down, and then we take a vector in this direction, which is this guy over here, and scale it up or down, eventually we can find scalars for each direction that are going to total up to the 125 newtons. So that's how vectors work. Essentially, we can use our geometry and our understanding of geo and trig to find, and the sum of vectors to basically find the opposing forces here. So what does that look like? Well, the first thing we need to do is we need to find unit vectors in each direction of each wire. So the first wire is at a 45-degree angle, and therefore a unit vector in this direction would have the components 2 over square root of 2, 2 over square root of 2. So that's a vector that's 1 unit long in the direction of a 45-degree angle. For the B vector, notice it's going in the opposite direction, so we're going to look at that not as a 30-degree angle, but rather as a 150-degree angle. The reference triangle is 30, 60, 90. And there we can get actually the B components, negative square root of 3 over 2 for the side to side, and up 1 half. Again, that's 1 unit long, and clearly if you add a vector that's 1 unit this way and another vector that's 1 unit that way, that's not going to oppose the 125 newton force. So instead, what I'm going to have to do is scale these up, but I don't know by how much. So that's where, sorry, I forgot the vector C, by the way, a unit vector in the direction of C, it's going straight up, is just 0, 1. Okay, so now we got to scale them up. So if I add a scalar times the unit vector in direction of A, and then a different scalar times the unit vector in direction of B, then I can have two forces which should combine to oppose the 125. So I'm going to scale the vectors up and write an equation like this. Scale up the vector in the 45-degree direction, plus scale up differently the vector in the 30-degree direction, and you will eventually have 125 times the vertical force you need. So one vertical direction, the unit vector, 125 times, is a vector that's 125 units long in magnitude. This creates a linear system because we have alpha times the square root of 2 over 2 plus beta times negative square root of 2 over 2 equals 125 times 0. And then I also have alpha times square root of 2 over 2 plus beta times 1 over square root of 1 over 2, and that's going to equal 125 times 1. So this is a linear system with two variables, so I'm just going to use elimination. Now, because of the ugliness of these numbers, I'm going to use elimination twice rather than elimination substitution. You'll see what I mean here. First, I'm going to double both sides of the equation to get rid of the fractions, and I'm going to take the opposite of everything in the first equation so that I can add these together. So you add these together, and they zero out, so there's no more alpha. We add square root of 3 plus 1 times beta equals 0 plus 250. Again, remember, I double both sides of the equation to get rid of the fractions, which makes my life a little easier. Now, to solve for beta, I just divide both sides by 1 plus the square root of 3. Now, remnant of the old world, you're supposed to rationalize this denominator. It'll eventually be expressed as 125 times square root of 3 minus 1. To me, personally, I would stop right here. even if it means losing one singular point, just because the extra time it takes to write this in a different form. Just put it in a calculator if you want to know the value, but this is exact, so it's fine by me. Instead of taking the beta as 250 over 1 plus the square root of 3 and putting it back into one of these equations to find alpha, I'm just going to do the elimination method and eliminate beta again. So to do that, I'm going to multiply the top equation by 2. I'm going to multiply the bottom equation by 2 times the square root of 3. So I get an extra square root of 3 here, an extra square root of 3 here, and then 125 times the square root of 3 there. Or 250 because it's doubled. Notice purpose of that was to get the square root of 3 in front of the beta to be opposite the negative square root of 3 in front of beta in the earlier equation. So then I get square root of 2 plus square root of 3 times the square root of 2 equals alpha. That's square root of 6, by the way. But instead I factored out the square root of 2 and then divide both sides. And I get this number. This is a messy number also, and again, it's not rationalized denominator, so it's technically not the right form. But nonetheless, what we need to understand is the scalar that pushes up against the a vector is essentially the force. It is literally the magnitude of the a vector, and therefore that magnitude represents the force in the direction of 45 degrees. This number here in front of beta is the force in the 30-degree direction, and so this is the tension on the beta wire, and this is the tension on the alpha wire. So that's the gist of this in a nutshell. The important thing is that you can recognize what the problem is asking, and the idea is when it says equilibrium, it's essentially saying the sum of the upward vectors should negate the total of the downward force. Recognize then that unit vectors in each direction are helpful because then your scalar of those unit vectors becomes the actual magnitude of those vectors and therefore the force that's opposing the traffic light. I hope you found this helpful. Have a great day.